Further, if you recollect, in classical mechanics, we have the coordinates qi of t, and of course also the moment as pi of t, and then they are replaced by phi of x mu or y of x mu. Okay, so therefore my classical mechanics was a classical field theory for me in zero space one-time dimensions. And here, if my mu takes value 0, 1, 2, 3, then this would describe my field theory in one time and three space dimensions, right? And then we go from here, we go to next further generalization, namely we introduce the fields x mu of tau sigma, phi mu of tau sigma. Okay, then this we will talk about it later when we, but essentially the same way, using the same definitions that we used to use in classical mechanics, a partial derivative of a Lagrangian with respect to velocity, and then in field theory, pi of x mu is over del 0 of x. So this is also del over del of phi. Okay. Just the same way in my string theory, I would have pi mu of tau sigma, which I would derive as the partial derivative, or essentially exactly the same way. Here I have put downstairs, so x mu. This is the function of tau sigma. Here I would appropriately define the Lagrangian if I write it as d2 sigma and L. Okay, all right. So it would for me define everything. Okay, this is, I mean, exact analogy. We have to first really grasp this. We had talked about it last time, but I thought these are some key points of string theory and we must consolidate them, and then everything would make sense. Otherwise, we proceed and maybe it doesn't make sense. So this is what we get, and this is what is called as the Oldenburg action. Okay, and this is for, we will see that it describes D-Branes. So we will go into more details of why we call it D-Brane. Okay, but at the moment we just take it, assume that like the zero brane described zero-dimensional objects, D-Brane are describing one-dimensional objects. So we have one extra spatial dimension that this x mu has got. So x mu of tau, now we have x mu of tau. Now whatever stuff we used to do with field theory, we can do with the string field theory. So string theory for me is just string field theory with one-dimensional fields. Okay, and right now we concentrate only on bosonic fields. X mu, we are at the moment not yet talking about superstrings or fermionic strings, but only about bosonic strings. So I can say that we describe these fields are having one-dimensional, one space dimension. That's all. Whereas in the conventional field theory, there is zero space dimension. Okay, all right. So now we are ready to talk about this particular action. What is this action? What can we do with this? What are its symmetries? Okay, and can we reduce this to the Nambu-Goto action, which we just wrote down earlier, involving a square root? Yes, under some so-called conformal gauge, I can reduce it to the Nambu-Goto action. So classically, one can say that classically they are equivalent. Okay, and then we look into the symmetries of this action. Okay, so this by no means, this is not a derivation of this action. This is just an intuitive pedagogical way of trying to understand the analogy, how, I mean, what kind of generalizations are involved in our in the subject of string theory. Okay, so this, I think, Lambert is just okay with here. Okay, good. So now we can proceed further, and now in this Polyakov action, d2 sigma, where L is minus t by 2 square root of minus h alpha beta and g alpha beta. Okay, and now we try to see what is this, what does it mean to us. So this is defined as del alpha x mu, del beta x mu, eta mu. Okay. And now there are two things. One thing is this eta mu nu I can write by two different notations, just like gamma mu nu, just to differentiate. Okay, if it is a function of x mu, or this is just equal to eta mu nu fixed. Okay, fixed means, for example, minus 1, 0, 0, plus 1. Okay, then my eta mu nu would be the inverse of this, would also be the same. Alright, and whereas this is more general. Okay, so this one describes the curved space-time and this one would describe flat space-time. So this flat space-time is a special case of this one, which is more general. Okay. Now, one more thing is that this H alpha beta, I am just considering various aspects of the Polyakov action at the moment. So this auxiliary field H alpha beta is conformally related to G alpha beta. And in fact, it is found to be just proportional to I should write it upstairs. So G alpha beta. And in fact, it is, so if you remove this tau sigma, this is the proportionality factor, let me call it beta. So that H alpha beta is B beta of tau sigma times G alpha beta. Okay, and the special choice of beta equal to 1 is called conformal gauge. When we take beta equal to just 1, this is conventionally called as conformal gauge. And in conformal gauge, this is just equal to G alpha beta. And then if we come back to the action and we take minus A by 2 into B2 sigma into square root of minus H into H alpha beta into G alpha beta. So this in the conformal gauge, you have that G alpha beta and H alpha beta in conformal gauge. Oh, I always make slips. So H alpha beta is just G alpha beta. So you see H alpha beta, it's the H alpha beta inverse. Okay, this is the inverse of H alpha beta. So here H alpha beta is G alpha beta. So this is actually the inverse of each other. And so what happens here, H alpha beta into G alpha beta is a unit matrix. Okay, and what you have here is minus T by 2 D2 sigma square root of minus H, and this is minus T by 2 D2 sigma H alpha beta, or this is equal to minus T by 2 D2 sigma minus, and this is nothing but your number photo action. So what we have done is, by going to the conformal gauge choice, under the conformal gauge, which amounts to setting beta equal to 1, gauge choices are always done by hand. Okay, they are arbitrary and ad hoc, but they go by some logic. Okay, so if we choose that gauge, conformal gauge, this is just equal to this, and this we know is our earlier known action, which we had written by writing the action in terms of minus P dA. This was minus P, and this was minus determinant of G alpha beta and B2 sigma. So essentially you recover the Nambu-Goto action from the Polyakov action under the so-called conformal gauge, and you can say that okay, classically they are equivalent. Now you would also, because we have spent enough time on relativistic point particle, you might like to see, can I reduce my Polyakov action to of one-dimensional objects to the zero-dimensional objects, or can I reduce D1 brane action to D0 brane action? How? Just to see analogy what we are going. So you can get it this way or you can go this way. Just going stairs up and down. Okay. So for going from we would like to reduce D1 brane action to D0 brane action. Let us see what we get. So my G alpha beta, G tau tau, G tau sigma, G sigma tau, G sigma sigma. Okay. We are in a two-dimensional worldsheet space. In two-dimensional worldsheet space, my alpha and beta take values 0 and 1, okay, for two-dimensional space. For two-dimensional world city space, alpha and beta are taking values 0 and 1. And let me again repeat that the index in x mu, okay, in x mu is taking value 0, 1, 25 or 0, 1 up to 9 for bosonic string and for harmonic or superstring. Okay, all right. We will talk about it. How do we fix this dimension? So here D is 0 plus 9, which is 10 dimensional for harmonic string, and D equal to 0 plus 25, so it's 26 dimensions for bosonic. Okay, they would be determined much later. How do we determine them will come much later. Okay, but right now we assume that this is some space defined by in 0 plus 9 dimensions, and this is defined in 0 plus. So right now we are not even talking anything about harmonic string. So we are talking only about harmonic strings, and here mu will always take 0 to 25. Okay. And one more simple thing is, wherever we have x mu, for example, or g alpha beta, for example, or h alpha beta, so now how do we understand these objects in terms of the target space and in terms of the world sheet space? Because we are here in string theory, we have two spaces, world sheet space and the space time space or target space or manifest space time, whatever you call it. As long as you see the index mu there, then this is mu vector in the target space. Is a mu vector in target space, and this is a scalar in world sheet space. Okay. So x mu is a mu vector, just like what is your a mu, electromagnetic field vector, a mu. This is a mu vector, right? When we introduce 4 vectors, concept of 4 vectors, Führer vectorial, yes. So this mu is a 4 vector. Similarly, here mu is a mu vector, but in the target space. Okay, and this would be scalar in the world sheet. There is no index alpha beta here, which spans my world sheet space. All right. So now what about H alpha beta? This has no index mu. So this is a scalar with respect to the target space, and it's a tensor to second rank tensor. In the world sheet space. Is this okay? This is the all right. And now after knowing this, we again go back to our this idea. Now let me make use of another colored pen, and I want to go from D1 brane to D0 brane. So for D0 brane, I would have G alpha beta would just be G tau tau. It would be a one element matrix, 1 by 1 matrix, right? G tau tau. And so with this my L would go to minus t by 2 square root of minus h alpha beta g alpha beta. This would go to minus t by 2 square root of minus h tau tau g tau tau, right? And this is minus t by 2 determinant of h tau tau and h tau tau into eta mu nu del tau x nu, right? G tau tau, okay? And this is, you can write as x mu dot x nu dot eta mu nu, and this I could write as x mu dot, or I could even write it as x dot square, okay, just to identify it with our, and this is your, so this goes to minus t by 2, and this is determinant of, so it remains to be the minus determinant of h tau tau and times this is right. So you can already start seeing its analogy with your relativistic point particle that you had for relativistic point particle or D0 brane. You had this to be 1/2 square root of e square into e to the power minus 2 x nu dot x nu dot. You remember this from our earlier considerations. In my notations, this was s was equal to 1/2 d tau into determinant of g. No, this was determinant of g tau tau into g tau tau, and this was x nu dot x nu dot, okay, and we had ignored here the term minus m square, okay, for the